So the fourth one is the product law, and it says if you have two different functions as a product, working as a product, and if you find the limit of that product, it's actually the same if you find the limit of those functions separately and then multiply that. Okay, so that means it says limit x tends to a, f of x, g of x, oops. So we're trying to find the limit of this particular product, right? So instead, we can do this. We can find it separately. So this is the limit of the first function. Oops, someone in the waiting room. Sorry about that, because I have to let him in. All right, yeah. And then we find the limit of the other function and then multiply it. There you go. So this is the law. It's the fourth limit law. And again, we'll see one example of it. They don't have any, so I have to generate one. Let's see whether I can generate a very good one. So let's say f of x is, I think we can use the same example we had the last time, something like that for x plus 7. Without changing anything, we can keep repeating that. Oops, someone saved a message. Now, really? I purchased the book. I don't have the book yet. Okay, let's talk about after the class, Ashley. Okay, g of x is, let's say, 3x minus 5. Okay, you can try this. So first of all, we want to find the limit of the product. Let's say at x equals, let's say at x equals -1. I guess we have already tried x equals 0 and 1. Let's try -1 because we can actually literally try for any value. So to find the limit of the product of 4x plus 7 times 3x minus 5. So our first job is to find the product. So the product is, what could be the product? Anyone?
12x squared minus 20x plus 21x minus 21.
Minus 21, are you sure?
Minus 35, sorry, minus 35.
Yeah, exactly. Thank you. Yeah. So we have just found the product. Is there any question? How did I get that? Anyone? If you're wondering how did I get that, let me know. No worries, okay? Any question from this, anyone? All good? Okay, let's carry on then. So now, since plugging in -1 isn't doing any harm to the function we have, to the expression, I would say, or function, you can say function as well, no worries. It's keeping our function defined, so you can straight away plug in the value of x, that is -1, not the value of x, the value which towards which x is approaching. So we can plug in -1 now. -1 squared minus 20 times -1. Oh, I think we can, sorry about that. I think we can rewrite it as
Yes.
positive, right? We can rewrite it as positive.
That's the plus x.
Did you say anything?
Yeah, that's it. My minus 20x plus 21x plus s.
Yeah, that's what I did here. Yeah. Okay, and this would give us 12 minus 1 minus 35. So minus 36 plus 12 minus 24. So this is what we get from the left-hand side. Now let's try the right-hand side. For that, we'll find the limits separately. So x tends to -1. F of x is 4x plus 7. Excuse me. Okay, and again, it's a linear function, or in other words, I can say that plugging in -1 isn't doing any harm to the function, so I can straight away plug it in. So -1 plus 7, it gives me -4 plus 7, which is 3, right? Similarly, we can do it for the second function, which is 2x minus 5. And again, for the same reason, we can plug it in here, and it gives us -5. So it's -3, -5, which is -8. Now, in the right-hand side, on our right, we have the product of those two limits, right? The products of these two limits. So we can now multiply those two. Multiply these two, right? So the product of these two, -1 f of x times limit x tends to -1 g of x, it gives us 3 times -8, which is -24. And this is exactly what we had here. Any question from this? Anyone, any question?
Could you do
this might
this?
sound like a
Oh,
stupid
sorry.
question, but how did you get the -24? So when I added it together, I got -48.
Can you see the calculation I have on the screen?
Yeah. So what did you do with the -1 squared?
So -1 squared is technically +1.
Yeah, but wouldn't it turn the 12 negative because you're multiplying by negative? Oh, it's +1.
Right, yeah. Because anything squared means you are multiplying it twice.
Yeah.
So this negative
I got-
gives you +1.
Sorry, that was just my
No,
calculator.
no problem, no problem.
Okay.
This is good that you are trying, and a quick reminder that I might do a mistake in the calculation. So if you see anything that's not matching with your work, that you think there could be a mistake, don't hesitate. Okay.
Okay. Thank
Yeah.
you.
Thank you. All right. Yeah, I think someone else was trying to say something as well.
Is this function right here, or this type of function, is it constricted to only 2 products, or could you do more than 2 products along this?
Very good question. Yeah, you can do it for more than 2 products as well. Yeah.
Okay.
Definitely. All right. Next one is slightly tricky, because so far we have seen, I guess, some difference and product law, and we can actually extend it for any number or any function, as long as it's not really harming to the function, it's not really making it undefined. So for the quotient one, the fifth law, we have a fraction now, right? And if you remember, I think we discussed it really briefly the last time, that whenever you have a fraction, your denominator can't be 0. Do you remember? I actually said it when I was discussing the topic, or not really topic, the definition of domain. For a fraction, your denominator can't be 0, because if your denominator is 0, then it's actually making your function undefined, which we don't really want. Same goes for this quotient law. Since you have a fraction, you can only use that as long as your denominator is not 0. I mean, your denominator is not approaching towards 0. Okay, that means, in other words, if you plug in the value of x, which it's approaching towards, if it's not making the denominator 0, then it's fine, we can use it. But if it's making it 0, then we can't really use this. Okay, we'll see examples. Maybe we'll see some examples like that. But yeah, you will see if you start practicing from the book or from other different sources, if you somehow see that by plugging in the value, you are getting a 0 in the denominator, then you can straight away think that you can't really use that law. Okay, that's the shortcut. All right, let's see one example of that as well. So this law says, again, as long as the denominator is not 0, that means for x tends to a, your function is not really approaching towards 0, you can use this law, which is finding the limit of a fraction is actually the same as finding the limit of two different functions and then divide it. I mean, and then find the ratio of that. Okay, it's the same thing. Again, your limit extends to a g of x. I mean, the denominator can't be 0. Okay, and we can find the same. We can use the same two functions, which is 4x plus 7, 3x minus 1. Let's see. I think it will work, because it will not make, yeah, I think g of x is not 0. We already have it. It's -8. Yeah, so I think we can use it. So now let's try the left-hand side first. So 4x plus 7 and 3x minus 5. Again, we're trying to see whether plugging in the value, sorry, I think I should plug in -1 here, sorry. Okay, now the first thing we want to see or check, if we plug in -1 in place of the x's we have, is it making our function undefined, or does it actually keep the function intact? So if we plug in -1, let's see what happens. We already know the values, don't we? It's -24 and -8. We have already calculated it here. Oh, sorry, +3 and -8, my bad. It's actually +3 and -8. So that means it gives us -3/8. Now let's try the right-hand side. So we already know what's the limit for f of x and what's the limit for g of x. We have already calculated it and it's actually the same. I don't think it's a good example, to be honest. It's actually very good for more complicated ones. Okay. All right, so any question from this?
Can
So if-
you? Okay, sorry. Go ahead.
If the limit, so if x is approaching 0, would we not be able to use this strategy and our answer would be undefined, or is there another way to figure it out, or is this just one, you know?
For this problem, if x tends to 0, I don't think the denominator will tend to 0. We'll still have a value, I believe.
Oh yeah, that's right. Yeah.
I guess we'll have a 7 over -5, right?
Yeah, but so if, well, I guess what I was asking is, say for instance, we just had like a simpler function or like a 3x or something like that,
Mhm.
where if we were to go to 0, the denominator would be 0. And would the answer just be undefined, or?
Oh, okay. So that's a good question. Yeah. So the limit could be 0. The limit could be undefined. It doesn't really mean that we must have a limit. So often you will see the limit does not exist. But if you just plug in 0 or any value and see that it's giving you an undefined value, it doesn't really mean that it has to be undefined. There is at least one law which you can use and check, uh, because using that law often gives us a defined value. We call it the L'Hopital law. L'Hopital law. It's written like this. It's a French word. If you have ever seen it, we call it the L'Hopital law. You will see it, I guess. If not today, you'll definitely see it tomorrow, I believe. Using this law, we often get a defined value, whereas we actually got an undefined one when we started. So yeah, to answer your question, yeah, definitely our limit could be undefined in the first place, but using some other formula or other methods, we can actually get a different value. But it's not guaranteed that you will definitely get a defined value if you use these laws. You can still get an undefined value for some functions. And I really like it. The L'Hopital law is really cool. I guess most of you will like it. It's really simple and it makes your life easier. Hopefully we'll see it soon. All right, what's next? Okay, the power law. All right. Okay, so it says, it's number 6, I believe. Number 6, the power law says, if you find the limit extends to a of a function of, or rather with exponent n, it's actually the same if you find the limit separately like this, oops, sorry, and then extend it to the power n. It will give you the same result. Okay. And let's try one example of it as well. I have to generate one so that it doesn't become bizarre. F of x to the power n. Okay. Let's try the smallish one. Let's say f of x is 5x. 5x, okay. And we're trying to find the value extends to, let's say, let's try half when 5x squared. Let's see whether it satisfies our law or not. Okay, so first of all, we can simplify it. So it will give us 25x squared. Okay. Now, a quick question. Can you see any law from the laws we have already seen? Can you see anything that we can use here? Anyone?
Product law?
Product law, yes, we can do that. We can actually do one even more precise.
Constant?
Constant, yeah, because we can actually write it like this, because 25 is a constant. Oh, sorry. We can actually keep it outside like this and find the limit of x squared, right? It's the constant law, constant multiple law.
I think we can use. I think we can use power law to.
This is the power law, by the way. I'm trying to show an example of it. So if I plug in half, oops. If I plug in half in place of the x, it gives me half squared, which is 1/4. So I have 25/4. Okay, let's see the right-hand side now. It says we can find the limit of the function and then upgrade it to the exponent we have. So let's find the function. Let's find the limit of the function. X tends to half. If you don't understand my handwriting, just let me know, okay? So 5x. And if we, again, we can use the constant multiple law, or if you want, you can use the product law as well, but I guess constant multiple law is the more, is I think, no, not the more, the better law to use here. So 5 times half, 5/2. And now it says we can actually upgrade it to a square. Let's see that it actually gives us the same result. We have 5/2 for this part, okay, from here. So if we square it, we get 24/4. Bazinga! Yes, it's the same, right? As you can see. One more thing I should have said the last time. If you have any problems with the colors I'm using, please let me know. Okay. Somebody might have a problem with the color, so I'm more than happy to avoid it. But if you have no problems, I'd like to use it so that it looks more looks easy. Because if I keep using the same color for different arrows and all that, it might look clumsy and more sophisticated to find out what's going on. But yeah, if you have any problems with any of these colors, just let me know. Yeah, any question now?
Are we allowed to choose whichever process we think is easier for ourselves, or do you want us to be using specific processes?
No, absolutely. You are allowed to choose. Absolutely.
Okay, thank you.
But yeah, just a quick reminder, if you use any of the laws, just make sure you have it in the side notes. I mean, just let me know that I know the law definitely, but so that I can understand that you actually know and understand the law, just have it just beside the line. Let's say like this, I have used the constant multiple law in this line, right? So I'll rather have a side note here like this. That hey, I have used the constant multiple law here. Okay, just let me know if you are required to show your work. Otherwise, you don't even need to show anything. Often you'll see some questions where you need to show your work. So on those cases, you can use the laws and write it like this. Just keep a side note that I'm using this law. Otherwise, if you don't want to use it, you're more than okay. But these laws are here to make our life easier. You will see examples. If you use this law, it will be solved within 2-3 lines. Whereas if you don't use it, it will take more time. Anyway, again, whichever looks easier to you, definitely. Okay, any other questions? No questions at all? Okay, so let's see the last one, which is the root law. It's actually not exactly, but quite similar to the power law, because the power law gives you something, in whole. That means a whole number, whereas the root law will have a fraction, but it's eventually the same because it's working as the exponent, right? But one thing you need to see is this other requirement you need to have, which is the function has to be positive for all those x's near a if your exponent, or the root, I would say, if your root is even. And why is that? Can anyone tell me? Let me ask you the question again. Let me write it for you. It's a really interesting question, I would say.
If you try to take the root of a negative number, don't you get an irrational?
You get an imaginary number.
Exactly. You get an imaginary number. Yeah, very good. I'll come back to it. Let me write it for you. So limit x tends to a for f of x. So it's saying that if you find the root, nth root of it, and then find the limit, it's actually the same as if you find the limit of the function and then find the root of it, nth root of it, of course. Now again, if n is even, sorry about that, what's that, Walgreens? Okay, so if n is even, then they're saying that your f of x has to be positive. And the reason behind it is simply if you have something negative, let's say, let me show like this. So let's say your f of x, well, this actually is for x near a, okay, where x tends to a, okay, or in other words, x is approaching a. It's not for everywhere anyway. Okay, so let's say if you have x squared, I'm just showing an example of why it's required to have a positive value for an even root. Okay, let's say I have x squared equals to -4. Can you solve it for x? So if we take the root on each side, what happens? Can you get anything defined? Obviously, we are talking about real numbers. We're not really considering anything imaginary. Can we get any value, any defined value for it? Anyone?
No. You get 2i, I think.
Yeah, we do get 2i, but that's still imaginary. So the point is, you can't have anything negative inside the root when n is even. So that actually gives us an idea that it is possible to have negativity when you have an odd power. Let's see that as well. Let's say I have a -8. So if we try to find the root, we'll go for 1/3, -1/3, a -8 of 1/3. It gives us -2. That means x is -2. We can have a solution, okay? So this is why it's really a necessary condition for a root with for an even root to have positivity or rather non-negativity inside. I mean, when you're trying to find the root, because you can see we actually can have negativity when the root is odd, but it's not possible when the root is even. Okay, any question from this? Any question that is kind of bothering you, that doesn't look good to you? No questions at all? Very good. Let's move on. The next one we have is the polynomial function and the rational functions. Okay, so theorem 2.4, it says if we have two polynomials, p and q, where x is approaching towards a, where a is a constant, then you can plug in the value in place of x in the polynomial. And the rational function says if you have a fraction, you can actually plug in the value of the value x is approaching towards, as long as your denominator doesn't become 0. I have actually said it, and I have already used it, to be honest, right? Can you relate to any of the problems I've used it? I guess for the quotient one, I've already used it. Yeah, here we go. This is exactly the example you will be looking for the rational functions. The denominator is non-zero, so I can plug in the value x is approaching towards in place of x, and it will give me my desired result. That's what the rational function theorem is saying. Any question from it? Anyone? Any question? Again, it's only true, or it's only applicable as long as the denominator doesn't become 0 if you plug in the value. If you plug in a in place of x, whatever the a x is approaching towards. Okay. No questions at all? Okay then. And for the polynomial, I think we have already used it as well. Yeah, here. This is the one. This is the example of a polynomial. Polynomial functions. This is a polynomial, and I have plugged in the -1 in place of the x. This is what the polynomial function theorem is saying. Okay. Any question from this one? Anything, even if it's really, really, really basic question. I mean, how does a polynomial look like, or anything like that? Don't hesitate to ask any question if you have any. All good? Okay. Let's try 2.3 now, which says limit laws for one-sided limits. Before that, am I going too fast or am I going too slow? Any suggestions?
I think you're doing a great pace. I think it's a good pace.
Thank you. If you think that I need to change the pace, just let me know. Okay, so 2.3, it says when you're calculating the right-sided limit, where is that? Yeah, it's basically two parts of this root law, what we have already seen in number 7. So it is actually subdividing this law into two parts. It's saying that if you are calculating the right-sided limit, then you can use it. And if you're calculating the left-sided limit, you can still use it, but only this condition gets changed. Okay, so let's just see that. So for 7, we had, let me write it for you again so that you can eyeball the entire screen. It's the root. It's the same as this. Okay, so this is the root law, number 7. We can actually subdivide. Okay, let me write the condition as well. It has to be, sorry, it has to be positive near where x is near a when n is even. Okay, now we can subdivide it into two parts. For the right-sided limit, let's avoid a because we are already using a for the value x is approaching towards. So let me use a Roman numerics instead. So let's say we are calculating the right-sided limit. If you remember, this plus sign signifies that you are calculating the right-sided limit, right? Okay. And, oops, sorry. And f of x is this. We have the root. So you can see we are actually doing the same thing, just we have changed it to from x tends to a to x tends to a plus or a positive. That means we are calculating the right-sided limit, nothing else. But you will see the condition will get changed. So this is when f of x is greater than 0 or equal 0 rather, for x near a, but x has to be greater than a as well. Obviously, n has to be even. Because for n odd, we have already seen there is no problems with that. But for this one, x has to be greater than a. Can anyone tell me why? Just try to imagine, how do you calculate the right-sided limit? Just try to visualize that. Anyone?
Wouldn't you include, I guess, maybe the positive integers, maybe? Coming from the right side, right?
So it doesn't need to be integers, to be honest. You can still have fractions, but why x has to be greater than a? Initially, for the main formula, main law, we said x has to be near a. That means it could be less than a, it could be greater than a. As long as it's pretty close to a, we're doing fine. But on this occasion, we're saying, no, we have one more condition to satisfy, that is the x, obviously it has to be near a, but precisely it has to be greater than a. Why do you think it's the case?
If it was less than a, would that include the negative numbers?
No, let's say I have a graph like this.
Is it because it's coming from the right side?
Exactly, it's coming from the right side. You're calculating the right-sided limit. Okay, we'll come back to it. So let's say we're calculating the limit as x tends to this point. Let's say this is my a, and we're trying to find the limit when x tends, since this is a right-sided limit, we're actually coming from this side, right? So whatever your x is, it has to be somewhere here, right? So this is precisely greater than a, because on our right, it's definitely the value is getting bigger. Since we're approaching from the right, it has to be greater than a. Obviously, it has to be near a. It's actually approaching towards a, so it will be pretty close to a, but it's going to be greater than a since we're approaching from the right. And if we're approaching from the left, to answer your question, you can see there could be positive values as well, because here is 0. Excuse me. Excuse me. So here is 0. We still have some positive values here when you're approaching from the left. Can you see that? So when you're approaching from the left, it doesn't mean that you will have a negative value all the time. You can still have positive values. Right? Any confusions? Anyone? Excuse me. And same goes, the same reason goes for the second one. When you're calculating the left-sided limit, you can clearly imagine your x has to be here, right? X has to be onto the left of a. So that means, in other words, x has to be less than a when you're calculating the left-sided limit. Any question from this? No questions at all? Okay, so for a couple of minutes, I want to share my screen again. screen of my computer. Can you see the screen now?
We can see, yeah.
Yeah.
Now let's see this example and let's see what we can do and what are the conclusions we can draw from it. Okay. All right. So this is a function. First of all, what type of function is it? What type of function it is? Can you see that? Can you just eyeball the function and say that it is this type of function? We have already discussed the name of it.
Piecemeal function or piecewise function?
Piecewise function, yeah, very good. So you can see we have more than one piece here, right? More than one piece is here. So this is a piecewise function. And as I said, if you remember, for each piece, you will have a certain value of x. You will have certain values of x, I would say. Like for this example, we have x is strictly less or equal 1 for this first part, and x is greater than 1 for the second part. Okay, I think we can, yeah, we are good to take a break of 5 minutes. I will start from here. It's 10:07, so we'll start at sharp 10:12. Okay, I'll see you in 5 minutes. Okay, we are back. And I'll start sharing again. Okay. All right. I should have paused the recording as well. Anyway, I'll try to do it from tomorrow. All right. So we have two pieces, and for each piece we have a certain, or rather we have certain values of x. So if we graph it, the graph looks like this. Fortunately, you will not be asked to draw this graph. At least I would not ask you in any of the exams, hopefully, if I don't get carried away. So the graph will be here, and all you need to do is to calculate it by just eyeballing the graph, if the graph is given, of course. All right, so you can see the first part is actually defined for x less or equal 1. So we do have a defined value. You can see this bluish circle. It's giving us an idea that at 1, we have a defined value for this, right? And the next one is defined for x strictly greater than 1. That's why you can see we don't have a defined value here. There is a hole here, right? Can you see that? So now if we try to calculate the limit when x is approaching towards this value, that means x is approaching towards 1, what's the first thing, or what are the things we need to do? Anyone? I'm trying to find the limit when x tends to 1 or when x approaches to 1. What are
You check the left and right hand and see if they match.
Very good. So we actually calculate the left-sided limit and the right-sided limit. And if they match, if they're the same, we say that's the limit. If they are not the same, we say the limit does not exist when x tends to 1 for this particular function, of course, right? Okay. All right. So let's try left-sided limit. We have already done this before. For left-sided limit, we start approaching from the left towards this value 1, right? This way. And our graph is taking us this way, right? Our graph is approaching this way. And when we go really, really, really close to 1, our graph goes really, really close to this bluish circle, right? So we say the left-sided limit is this. And if we can go to our left, straight to our left, or draw a horizontal line towards the y-axis, we can see it goes towards 2, right? So we say the left-sided limit is 2. Do you agree? Don't look at the solution. Just try to see the graph. Try to understand why it's 2. Don't just agree, okay? I might be wrong. Do you actually agree that it should be 2?
Yeah, they both approach the, looking at the graph, they both approach 2 on the y-axis, which is the what the function would be at 1, or going towards 1 rather.
From the left, right? From the left, it's actually going towards 2. What happens if we approach from the right? Let's see that. We're approaching towards this 1 from this side of the x-axis, and our graph is slowly and slowly going towards this. So
It's approaching 0.
Yeah, it's approaching 0. And why? You can see the line is actually on the x-axis. And we know that on the x-axis, the value of y is 0. Right? So this value, the right-sided limit is 0. We can just eyeball it from the graph. Now, before we go any further, any question, how did I get 2 as the left-sided limit and 0 as the right-sided limit? Don't just agree with me, okay? If you don't understand, just let me know. I'll try to convince you, probably by rephrasing it in any other ways. Excuse me.
I'm really sorry, but could you just rephrase the limit of f of x equals 0 again for that second function?
I mean the right-sided limit?
Yes, please.
Okay, yeah. So do you agree that when we are approaching from the right, our function is approaching towards this? Do you agree? This whole?
Yes, absolutely.
Okay. So what's the functional value at this point? That means if you have a graph which has a point on the x-axis, what's the value of y then? Y, in other words, is the functional value, right?
Right, yeah.
So what's the value of y?
It would be 0.
And why?
Because it's on the x-axis?
Yeah, exactly. Because on the x-axis, anywhere on the x-axis, the functional value, the y value is 0.
Okay. Although the point isn't filled in, so would that not actually be 1, but does it still count as 0? I'm just a little confused on that, the not filled.
Okay. So for the limit to exist, I mean the right-sided limit to exist, it doesn't need to have a defined value there.
Oh, okay.
We are actually approaching towards it, not really getting there. We are really, really, really close to that.
Oh, okay. Got it.
Right? Yeah.
That makes sense. Thank you so much. I appreciate it.
No problem. Okay. Now, a really, really quick question. What should be the limit of this entire function?
There is none.
And why?
It's because the left and right side limits don't match.
Because they are not equal, the left and the right.
Very good. Because for the limit to exist, we know these two values have to be the same. These two have to match. But we have 2 and 0. This doesn't really match, don't really match. So we say that when x tends to 1, the limit does not exist for this particular function. Any question now? Take your time and see if you have any question.
So when you like give us a graph like this, like if it was on a test or homework or anything, we wouldn't have to use any of like the theorems that we just went over?
No, when you are given a graph, you actually don't need any law. You can actually just eyeball it. And
okay.
Yeah.
Okay. Thank you.
Yeah, good question. Yeah. Any other questions? If you don't have any other questions, we can actually go for the next one.
Mr. Egg, I have a question. I have a question.
Yeah, sure. Go for it.
Okay, so if as in if we have about three the piecewise function you give us or anyone we meet in the homework on Pearson homework, if there are 3 graphs on a single line like this one now, we have left, right. If there are 3 graphs, how do we do it?
Yeah, I'll show examples like that. Yeah, you will have 4 or you can have 4 or 5 pieces of a single function. Yeah, you will have you doesn't necessarily have 2 functions all the time. You might have 4 or 5. So I'll show how to calculate all this as well. No worries.
Okay.
Okay, next. We have 2.17. Okay, all right. Okay, so we have two scenarios here. Okay, so we have a function for which at A there is a defined value, but on a different piece. That means it's a piecewise function. Let's say this is a graph of the first piece where x is not A, and for x equals A, we have a defined value here, whatever it is. Let's say that's f of A. So now the first question is, don't look at the right graph, okay? Just look at the left graph. The first question is there a limit? I mean, does the limit exist for this function? And why? Take your time, no worries, you know. You don't need to make a quick decision. The first question is, if the limit exists, whether or not the limit exists and why.
This is for the left-hand figure?
Yeah.
I don't think it exists because where it says y equals f of x, like the little hump or whatever, like the curve, goes above our point at f of a. So then it's like exceeding the limit, so it doesn't exist.
Okay, anyone else?
Yeah, it shows. I don't think it exists because f of s is not equal to f of a.
So f of a is actually a functional value. So for the limit to exist, we need to have the left-sided limit and the right-sided limit matching to each other. Is it the case here?
No.
Or for x approaching to a, towards a. What if I say when x is approaching to a, our left sided limit is this, whatever this value is, and our right sided limit is also this. Do you agree?
Yep.
So what if I say the limit exists? Do you agree?
So is this not a piecewise function, is it? No.
This is a piecewise function, yeah. But when we are approaching towards a, as I said, like for this one, we don't really need to have a defined value here, right? We don't need to have a defined value here. We are just approaching towards this point and see where does our graph is approaching. And from either side, I can see my graph is actually approaching towards this hole. And there is going to be a certain value here as well, whatever it is. Let's say it's g of a, or sorry, f of b, or something like that, or whatever it is. There is a value here. It's not defined for the function, but our function is approaching towards this from either side. Or in other words, my left-sided limit is this, my right-sided limit is also this. So what if I say the limit exists? Now look at the right hand or the right graph, whatever it is. So you can see they're saying the limit exists, and why? The curve is the same with the same hole at the same point. It says the limit exists. And why? The reason is same. You're approaching from the left, the graph is going here. You're approaching from the right, the graph is going here, to the same place, to the very same place. That means it's giving us same values for left and right sided limits. And that's why the limit exists. But we don't have a defined value there. Although, or rather, in the first graph, we had a defined value for A. We had a defined value for A. For this graph, we don't have a defined value for A. But the limit still exists. Squeeze there. Oh, that's a nice one. Okay, so the first question is, or rather not the first question, the first point is, you don't need a defined value at the point x is approaching to for the limit to exist. All you need is to have the same value as the left and right sided limits. So for both these graphs, our limit exists. But for the first one, we don't have a defined value at A. We have a defined value at A, rather, sorry. For the second one, we don't have a defined value at A. There is a hole, and that's it. We don't have any value defined for A, defined at A, rather. But for the first one, we have a jump. There is a hole here. That means the graph is not defined at A for this curve, but we have a certain other value here. There is a jump. We have a defined value for A, separate defined value for A. But on both occasions, our left and right sided limits are same. So on both occasions, our limit exists. Limits exist, rather. Do you agree? Take your time. We'll see more example and we'll come back to it, okay? Let's see the next one. And meanwhile, if you can think of a question, just let me know, okay? All right, the next one. The function is, the function is x squared minus 6x plus 8 over x squared minus 4. Okay, so we can see a hole there. And don't look at the right-hand side now. So for the left graph, why do you think there is a hole? Why do you think the value, or rather the function, is not really defined there? Why do you think it's not defined there? Anyone?
Is it because your equation there, if you plug
Would it be
in,
zero?
sorry, go ahead.
Go ahead. Go ahead.
I was gonna say, is it because if you plug in 2 to that equation there, it doesn't work. You get a 0 over 0.
Right, very good. So if you plug in 2, you can see it gives me 0 in the denominator, what we don't really want, right? Okay, so that's why there is a hole, because at 2, the function becomes undefined, so we don't have a defined value for 2. Otherwise, the function is defined everywhere else. Okay, so we can actually remove this hole. You'll see more of this when you work on the continuity. Okay, how can we remove this hole? So we can actually try to factorize both numerator and denominator. Let me show the show the right side graph. And once again, I'll share my screen. Again, things will start getting more and more complicated. So if you don't understand any of the things, don't hesitate to say that, okay? Okay, so let's see how can we simplify that. So we have x squared minus 6x. What is the function again? Minus 6x plus 8, okay. Over x squared minus 4, I believe. Right, yeah. Okay, now let's try to simplify it. So let's do it one by one step at a time. How can I simplify the numerator? Can you imagine anything from the college algebra course?
Yes, we can factorize it.
How? How can you factorize it?
That means we can break it to 2 by using factorization method.
Is that a 2 in the middle or on top where it says x squared? Is that 2x?
X squared
it's
minus 6x.
6x?
Yeah, pardon my bad handwriting. Yeah, 6x. It still doesn't look like 6, does it? Yeah.
So you have a minus 4.
So x is to be when we factorize it, we get x minus 2 bracket x minus 4.
How did you get that?
I mean, when we factorize it, when we find the coefficient of x, yes.
So if you remember this method, remember it? We had -6 and we had 8. So our product has to be 8 and our sum has to be -6. So we are looking for 2 values whose product will give us 8 and is it 8 really? Yeah.
What I mean is that if we factorize the numerator, then we're going to get s squared minus, looking for the coefficient of 6. 6 and 8, number that can go in 6 and 8, we use 2, then s squared minus 2x minus 4x plus 8.
Yeah, definitely.
So we're going to get x into x minus.
Yeah.
So we're going to get x into x minus 2 minus 4 into x minus 2. So we get x minus 4x minus 2.
Yeah, of course. So we are looking for 2 values whose product will be 8 and sum will be -6. So this is only possible for -4 and -2, right? So we can rewrite it as -4 and -2. This -6x can be rewritten in this way. And we have +8. And of course, for the denominator, we already know this formula, right?
Yes. So the other way, x minus 2 bracket x minus 2.
So this could be written as 2 squared. And if we factorize, we get x minus 4, x minus 2. Really, x minus 2? Yeah, I think so. And x plus 2, x minus 2.
X minus 2, yeah.
So we can cancel this out. And we can say that this is actually equivalent to the original function we had. This is actually the same as this. Okay. So if we graph this one now, we'll get this. Get the second function. There you go. Okay. Now we get this second function where we don't have the whole at 2. Do you agree? Anyone? Any question? Do you agree with me that?
My question is why we don't have a whole at 2 in the second graph? Because is it because it is minus half?
On the right?
Yes, if we plug in the second function, if we plug in 2, we're going to get minus half over 2. So is it because of this reason we don't have a whole?
So first of all, if you plug in 2, your denominator is not getting 0. So you don't have, or rather you can't have a whole. You can only have a whole where your function gets undefined. Like for the first one, if you plug in 2 here, your denominator was 0. If you plugged in 2 here. So that's why we had a whole at 2. But on this occasion, you actually, if you plug in 2, you can see the denominator is not getting 0. So that's why I don't have a whole. And about getting negative half, we'll come back to it later. But first of all, we want to see why, or rather, how did we actually get rid of the whole? You can see now if we plug in 2, it's not getting undefined. The denominator is not getting 0. That's why we have got rid of the whole. Okay. And the second part of your question is why, or rather, how did you get a negative half? It seems the questioner asked you to find the limit when the graph, or rather when x was approaching to 2. Now, I guess someone asked this question a couple of minutes back that if we get a 0 in the denominator in the first place, will it be undefined all the time, or can we actually do other, or rather follow other things to get rid of it? Now you have an example of it. So for the first function, if you plug in 2, you can see you get an undefined value. That means your limit does not exist, right? But if you can simplify it and reach this second version of it, can you please unmute yourself? I don't know, where is that coming from? The background noise. Thank you. Yep. So if you can simplify this to the next version, and now if you plug in, you can see we get a defined value. And these two are actually the same function. You have just simplified it, nothing else. It's not a different function, it's the same function. So even if you have an undefined value in the first place, you can modify it, you can use different formulas or methods to get a defined value. That's what I said a couple of minutes back, if you remember. So this is the same function. You started with an undefined one, but then you remember, hold on, I can actually simplify it. And then after simplifying, you can see that you actually get a defined limit. I mean, you actually get a limiting value, right? Now, any question?
Yep.
Any question? Anything that is still confusing? You don't need to agree with me all the time. Okay, you can have your say, and we can have a constructive argument with each other. Okay. That's really healthy. That's the healthy conversation is going to help us in the long term. No questions at all?
So just
my
to
question,
clarify, the left side, again, that limit right there is undefined because if you plug in 2, then that equals out to 0 over 0. But on this right-hand equation, it's -1/2 if you plug in 2.
Right.
Okay.
Yeah, any other questions?
so my question again is, now, you said the other time that if we plug in, let's assume we plug in the first equation, we plug in 2, we substitute 2 for x, and that means the denominator is gonna be 0.
Right.
So that means the function is not exist. So what if the numerator is 0 and the denominator is a digit number? What will you call that one?
Oh, okay. So you're saying the numerator is 0 for any value, right? It could be for, let's say, I think the numerator will be 0 for x equals 4. Yeah. So if you plug in 4, the numerator becomes 0 and the denominator is not 0. Is that your question?
Yeah, of course.
Okay. So if the numerator is 0, no worries, because 0 over something is 0, and that's still a defined value. That's still something we can have. If the numerator is 0, we have no worries. We don't have to worry at all, because 0 over something will be 0, and that's still fine.
Thank you.
We only care, or rather, we only have to be cautious about the denominator. It can't be 0, because something over 0 is going to give us an undefined value. But 0 over anything is not a problem, because 0 over any value is going to be 0. So no worries with that. Okay, any other questions?
I have one more. I guess if like we were doing the limit for x going to 4 or something, we wouldn't even need to go to the second step. We could just, find the limit in that case since the denominator wouldn't be 0.
Yeah, very good, very good. Yeah, you don't need to go for the second one if the denominator is not 0. You can only look for other methods only if the denominator somehow becomes 0. If the,
Okay, that makes sense.
yeah, very good question. Yeah. Okay, let's move on then. And finally, we are here to the secant and tangent line. Let's see what informations can we derive from it. Okay. Okay, so we have a graph for the function 2 to the power x. It's an exponential function. As you can see, it's getting in as you are moving towards your right, it's getting increased exponentially. So for this graph, we are looking for the limit where x tends to 0 from the right hand side. That means we are trying to calculate the right-sided limit when x tends to 0. And we're trying to see what's happening here, what is going on here. Okay. And for that, I want to show the screen. I have to share the screen again. Let me do that for you. Okay. Yeah. We are back. So yeah. For the graph of 2 to the x, it looks like this. First of all, let me draw the axis. Let me have it slightly below because it will never cross the x-axis anyway. And the graph looks like this. Okay. So this is the graph of 2 to the x. Not exactly maybe, but it's quite similar. And x is approaching to 0. That's our 0. X is approaching to 0 from the right. Okay. So that means if we are approaching to 0 from the right, our graph is approaching to this, right? And at 0, you can see it's, I mean, when we are really close to 0, you can see the graph is really close to this. Okay. All right. So no problems with that. Now what happens with the secant and tangent line? Okay. So as I said, for the secant line, you have 2 points. Let's try this one. If we add these two, I hope I can join these two. Oh, very good. Okay. So that's the secant line. Okay. And if you remember, if the 2 points converge to each other and go really, really, really close to each other, that secant line becomes tangent line. And that's what they have shown in 2.19a. Why? Let's see what happens. Let me take another point closer to 0, closer to that bluish one. Now if I add these two, I hope I can join this properly. Okay. And if I keep doing that, if I go more and more close, if I go closer, you'll see it's getting more and more sophisticated to draw. Okay. And what it means, eventually, when these 2 points will get really, really close, you will see, let me use another color. This one. You will see for this graph, it will actually be just touching this particular point and going like this, not intersecting the graph. And that is a tangent line. And all of the lines here were secant lines. So that's what they're trying to show. As you can see, if you have it open in front of you, that the secant line approaches the tangent line and the slope of secant line is approaching towards the slope of tangent line. That's what you can see, right? Since we are going closer and closer on this in this direction, you can see the points are getting closer, and eventually we'll have a one single point where the line will touch it and go through it. It will not have 2 points. If it's really, really close, it can't have 2 points, right? So graphically, we say if it just touches the line at one point, at that particular point, and goes through, then it's a tangent line. So that means if you go closer, the secant line goes closer to tangent line as well. That's what they're trying to show here. Any question from this? We actually discussed it the last time, I guess, but for some reasons they have shown it again. Any question from this? And same happens when you approach from the left. You'll have several points here, and you'll have secant points, several secant points going through this particular point, intersecting the graph at that point. But eventually, when you go really close to that point, you'll have a tangent line. And at a particular point, you have a unique tangent line. But you can have several tangent lines depending on several points. You know, if you consider several points, you will have one each tangent line for each of those points. Okay, but as you can see, for this particular point, you can have several secant lines for one single point, because you're getting connected to different points. Okay, I hope I made it clear. If you're still struggling to understand, just let me know. Anyone? Any question? No questions at all? All right. Sorry. Okay, so now let's move on to the next one. Let's see, what does it say? Okay, figure 2.20. We have the squeeze theorem now. It's really interesting, and it will help us to find limit where we can't really do it using any other methods. It will help us to find limit where we can actually make a sandwich. You know, how do you make a sandwich? You have two pieces of bread, right? You have two pieces of bread. Let's say that's the two pieces of bread, and then in between you put the cheese, right? And then you just touch those with each other like this. You squeeze them, right? And here is your sandwich. So this squeeze theorem is often recognized as the sandwich theorem. I hope I have the spelling right. Anyway, never mind. So let's see, what does it give us? Again, I have to change it to the screen sharing of my computer. Okay, here we are back to the computer. Okay, so the squeeze theorem says, let us see the statement first and we'll go back to the graph. So it says, assume the functions f, g, and h satisfying this. That means g of x is actually lying in between f and h. Okay, as you can see, it's actually in between f and h, like the cheese of the sandwich, right? It is, these are the two pieces of bread, and this is the cheese. So it's actually getting squeezed between these two functions for all values of x near a, except possibly at a. Then we say, if the limit of these two functions are the same, and say that's L, then we say the limit of this particular function is also L. So that means, first of all, we need to check a couple of things. First of all, the function we are looking for, the limit of the function we are looking for, the function has to lie between two other functions. This is the first condition we need to check. Second one is, we need to find the limit of these two functions separately. And if they match with each other, then we say the limit of our desired function is also the same. Okay, let's see the graph. Okay, so here we have two functions, f and h. F is the bluish one and h is the pinkish one. And you can see our function g is actually in between these two functions, okay? These two functions can actually hold this, not really hold, I shouldn't say hold, but this is actually creating a compact situation for this function g. Okay, or in other words, I can say this function is getting squeezed between these two functions, f and h. Okay, and now the squeeze theorem says if the limit of this function is, let's say, L, and if we can calculate the limit of f and it's also L, then we can straight away say then the limit of g will also be L. Okay. Okay, let's see this one. This one is really interesting. Okay, so we have a function which is x squared times sine 1 over x. Don't get scared. Okay, you'll not be asked to draw a graph like this. So the blackish one is the graph of x squared sine 1 over x. If you have a graphing calculator, or if you can use the graphing tool online, or maybe in any of the mathematical software in your computer, you'll see the graph of x squared times sine 1 over x will look like this. Forget about the red and bluish one, okay? Red and blue lines. So this is the graph of x squared sine 1 over x. And let's say you are asked to find the limit of that. It looks scary, isn't it? Doesn't it? So instead, what we can do, we can try to find two functions which can squeeze that, or rather our function, in other words, we can say our function will lie in between those two functions, and calculating the limits of those two functions will be much easier. Obviously, since we are trying to find such a function, we'll try to find a function which the calculating whose limit will be easier, definitely. And if the limits are the same, we'll be able to conclude that they have, our function also has the same limit. So if you draw the function of x squared and negative x squared, your graph of x squared will look like this, and the graph of negative x squared will look like this. If you draw it, it will, if you take if you take a couple of points, you will see the graph will look like this. Or obviously you can use the graphing calculator or any other graphing tools. So we can eyeball and see that yes, our function actually lies in between these two functions. Do you agree? No part of the function has actually gone beyond any of this on any of these curves. Do you agree? So we say that this function is squeezed between these functions x squared and negative x squared. So the first part is done. The next job is to find the limit of these two functions and see if they match or not. Okay. So if we are looking for the limit of these functions, let's say at 0. So when x tends to 0, the limit of this function is 0, right? And the limit of this function is also 0. Since they match with each other, we can say when x approaches to 0 or when x tends to 0, the limit of this function will also be 0. But when you have this function to start with, if you plug in 0 here, it becomes sine infinity. because 1 over 0, we can, for calculating limit, we can replace it with an infinity. So it will be 0 times sine infinity, which is going to be undefined. But using the squeeze theorem, we can see the limit of this function is actually 0 when x tends to 0. Do you agree? Any question from this? Any question? Anything that is not convincing enough? No questions at all? Okay. All right, let's see the last example, and I think we have 2 more minutes. Yeah, we can finish it then. Okay. So let's say we are trying to calculate the limit of sine x. Okay. So sine x can be written, or sorry, can be drawn, and it will look like this: the black curve. Okay, the black curve here. So this function can be squeezed between the function absolute value of x and negative absolute value of x, which is these 2 graphs. Okay, because absolute value of x is this one, the V-shaped one, and the negative absolute value of x is the upside down V. So clearly our function sine x lies between in these 2. So if we can find the limit of these 2, and if they match, we can say that it will be the same for sine x as well. Okay, same goes for this one as well. This is the graph of cosine x. This is only a shorter part of cosine x. You can actually extend it to this way and this way as well. This is the graph of cosine x from negative pi over 2 to pi over 2. And this can also be squeezed between the constant function h of x equals 1 and the 1 minus absolute value of x. This is 1 minus absolute value of x. Okay, this one, this bluish one. So this function cosine x definitely lies in between these 2. So again, using the squeeze theorem, if you can find the limit of these 2 for any x, for x approaching to any value, and if they match, we'll be able to say that this the limit of cosine x will be the same as well. Okay, any question from this? We'll actually do examples mathematically, I mean algebraically as well. No worries, okay? But does it make sense? How does it look? How a graph looks like when I say that it lies in between 2 graphs, or when I say it's getting squeezed between 2 functions? Does it make sense now? How does it look like to lie in between or to get squeezed? Anyone? Any question?
No, I think it's pretty explanatory right there. That graph really helps showcase it, I would say.
Okay.